Hi everyone, welcome back to the workshop, and it's project time. Well, kind of, it's repair time as well. And what you're looking at is my new Advantest R6581T 8.5-digit multimeter. I picked this thing up on eBay the other day and I got it quite cheap. I lowballed the seller, not thinking for a moment I get it, and he just wrote back, there, it's yours. So wow. So it arrived the other day and it works absolutely perfectly. As you can see, it's quite accurate. I've got a PDVS2 Mini connected to it right now, set to 1 volt, and it's quite accurate there. But there is one problem with it, as you can see. Let me zoom in a little closer. And that is that the VFD itself is actually quite dim. It's a notorious problem for the R6581 series of DMMs, and they no longer make replacement VFDs and you just can't get them. Everybody's holding on to them and they're falling like flies at the same time. So it just so happened that somebody on the EEVBlog forum, going by the name of Mickle T, actually reversed engineer the R6581, including coming up with a replacement OLED display powered by a STM32, and basically you just wire it up inside. There's no cutting of any tracks or anything like that. You just desolder the existing VFD, fit the new OLED display and the STM32, and it basically replicates the exact same display. It is a little bit smaller. If I can just grab a display, I'll hold it up. And here it is. As you can see, it's not the full width, so it's a little bit of a compromise, but given it is really dim in the first place, this actually makes a lot of sense. So in this video, I'm going to tear the meter down and get to work removing the existing VFD and fitting a new one. Now, of course, being a different size, I will need to make some sort of brackets, that sort of thing, to hold the new OLED display in place, and that'll be part of the project. However, before I actually fit the new OLED and the STM32 board, I do actually want to breadboard it on the workbench, because I've got a modification in mind for the new OLED display. And the reason for that is the new OLED is bright enough outside of the R6581, but as soon as you put it behind this smoked screen here, it can look a little bit dim. Nothing like the original VFD that I've got here, but I do want to modify the OLED and try and increase the brightness of it to give it as best a chance as possible the other side of the smoke screen. And before I do that, let's take a little bit of a look through Mickle T's project photographs that he posted. And you can see this is the rear of the display board. There's his STM32 board, and there's it picking up some signals from the back of the display board and then running off to the new OLED display there. And a little bit of a close-up there. It picks up some signals that drive the electronics that in turn drive the VFD itself. So there's some serial data that comes in from the microprocessor that is able to pick up that can run off to the STM32 board. And as you can see there, there's 3 or 4 wires there, some supply here and 3 signals there. So I'll be tapping into that exactly as you see here. And here's the front of the display board, and shows the new OLED display mounted in place of the original VFD. There's the pins along there where he desoldered the VFD. And he did actually provide a really nice diagram showing STM32 board and the wires tapping into those signals that drive the display drivers and the actual VFD itself. So really easy to follow. And then you've got a connector here that goes away off to the actual new OLED display. There's actually a number of people that have already made this conversion, and looking at it, as I said earlier, decided I wanted to try and do something about the brightness of the OLED display. And of course it's set to maximum brightness through software, but behind that smoked screen it's not quite bright enough in my mind anyway, and as other people have found out. So I decided to take a look at the actual electronics on the back of the unit and see if I could find out any more information. So what you've got here is the circuit board and the actual OLED display, the flat flex from it coming through onto this connector here, and it's chip on flat flex that you can see here. And down onto the circuit board you've got your user I/O connections over here and a few power supply related components on the board, because it needs to boost up 3.3 to 5 volts, 5 volts to 14 volts I think it is, for the actual OLED drive itself. So I went online and tried to find out what some of these components are, see if I could dig out a schematic, and I did find something. Now this is not quite the correct schematic for my board, but it's almost identical. You've got the actual OLED display here with that 30 pin flat flex coming down onto the main board. Over at the left hand side here you've got 5 volts coming in on the left hand side here. You've got a couple of 3.3 volt LDOs in parallel with each other, providing 3.3 volts for the circuit. And up top here you've got a boost converter which provides that 14 volt supply, which also goes away off into the actual OLED display. That's for the current drive for the OLED segments. Now I've never worked with these OLED displays before, so I wasn't really aware of the SSD1322 chipset features. That's that chip on the flat flex, so I didn't know much about these signals here. But looking along the line here, I came across this one here, iRef, and it's got a resistor, a 910k resistor down to ground. So I started looking at that resistor there. Perhaps this is a current control for the actual OLED itself. So I went off, found some other documentation which better explained what iRef was for. And from the actual datasheet for the SSD1322, I actually found this page which deals with the segment driving block. And there is on the diagram here the iRef pin with the resistor down to ground. And what you're supposed to do, as it explains here, you're looking to get 10 microamps of current flowing out of the iRef pin down to ground. So depending on what voltage you're running at, in this case on my OLED it's 14 volts, depending on that voltage you can adjust this resistor here to try and achieve that 10 microamps current. And what that does is it sets up a nice nominal segment current drive for each and every one of the segments on the OLED display. And down here it gives you an example. I think they've got 18 volts for the VCC, and looking for your 10 microamps iRef current, it calculates that resistor there should be 1.2 mega ohms. So what I'm going to try and do is vary that resistance to try and boost the segment drive current. And up here it actually tells you we're looking for an I segment current of 300 microamps. That's each individual segment is looking to have about 300 microamps through it. So if we can get that 300 microamps up a bit, we'll make the display brighter. Now it is an OLED display, and those are quite notorious themselves for basically wearing out. The segments will dim over time. I've experienced that myself with a small 1-inch size OLED display that I had running for just over a year, 24/7, always on, and after about a year it lost about half its brightness and the segments were actually quite uneven in brightness. So that IRF pin along here is actually on pin 22, and you can see they're numbered rather conveniently 1 to 30. So tracing back pin 22, it actually connects to R1 here, and measuring that one there will confirm what size it is and what size it needs to be in order to make it brighter. But for the moment, I'm going to leave it with the stock value, and let's hook it up to my R6581T with my breadboard, and let's look at the brightness it is, change out the resistor, and let's see what we can achieve. Now this unit here actually came from a rack system, because when I got it, it had a couple of rack mounting lugs on the front. So I suspect it was probably powered up 24/7, something like that. Hence the VFD just plain wore out. Now, I have actually already been in the unit. Decided to take a look inside it when I first got it, just to make sure everything was okay. Which it was. Right, let's turn it round and let's see if we can get the front panel off and flip forward. And there is the front panel disconnected. As you can see, there's just these two flat flexes here that connect to these two sockets down here, and that's it. No other connections. So next job is to go and solder up my test lead to the breadboard and pick up the necessary signals as I showed earlier on the diagram. Now here's the actual STM32 board that I'm going to use mounted onto the back of the front panel there. But I do actually have my test one here already plugged into the breadboard, already hooked up. I've got the OLED display connected up as well. The only thing I need to do is the other end of this cable here. Here's the 5 cores. I'm going to pick up the signals and the power from the back of the front panel. So I'll go way off and wire this up now. Well, there's the display board removed from the front panel. You can see the VFD there. Such a shame it's worn out, because it is actually a beautiful thing when you see them at full brightness. And there is the back of the board with my 5 connections hooked up away off to the breadboard. No cutting of any tracks. No need to remove the VFD at this point for my initial test. And I've got the breadboard sitting here with the OLED display already. So let me just go and put a power cord in and let's power her up. Almost ready for a power up, but one thing I just about forgot about is this little selection grid here, and there's a little table down there for selecting the mode that the OLED can run in. It's got 4 different modes, including 3-wire SPI and 4-wire SPI. And I need it selected to 4-wire SPI with R5 and R8 selected there. So you can see I've got them jumpered there. So we're ready for a power up. Okay, ready for a power up. Got the display board hooked up, the flat flexes, and it's positioned nicely there so that we can see the display. Got my breadboard and got the OLED display just sitting there. So let's power it up. Yes! Yes! It's working! And yep, we've got the same digits and information that's on the VFD now on the OLED display itself. Perfect. It is flickering every now and then. I'll put that down to my long cable, I think. And perhaps the breadboard might need some supply decoupling capacitors, possibly. But otherwise, it's pretty good. What about the brightness and the smoke glass here? Well, I think I should be able to offer it up inside here and position it so that we can actually see it. It'll be upside down, but I should be able to see it and see how good it is. And I'll put on power if I can. And yes, It's not bad at all, actually. Not sure what it's like on camera. It's not bright, so it could certainly do with just a wee increase in brightness. So I think I'll do that now with that resistor I mentioned earlier. So let's see what value we've got on R1 at the moment. That IREF resistor. 680k. Okay, that's definitely different from the paperwork, but I guess that every OLED display is probably a little bit different. Okay, so 680k. Let's try changing that and see what difference it makes. Okay, so I've actually gone ahead and hooked up my little Decade box. Hopefully that won't cause too much of a problem with the long wires, but we'll just give it a bash anyway. And I've got it open circuit at the moment, so we will power up and I'll just try out some parallel resistor values over that 680k and see what happens. Right, so I'm going to try 9 meg. No difference. 5 meg. No difference. 1 meg. Yes! I don't know if you can see that, but a 1 meg in parallel, and the brightness just ever so slightly increases. That's it off. Let me just zoom in a bit, see if we can capture that. Right, so I'll just try that 1 meg in parallel again. That's it off. That's it on. That's it off. I can definitely see a difference. I don't know what the range of that resistor value would be. Well, I think 1 meg in parallel there is about as low as I'd like to go. One thing I'm going to try now is I'm going to hook up some different colour OLEDs and view them through the front panel and see which one visually is the brightest. Okay, so I've got the lights out at the moment. I've got the white one behind here, a standard brightness. I've taken off that resistor for the time being, and let's just eyeball the brightness. Okay. And now I'm going to hook up the yellow one that I've got here. Oh, I'll take off the screen actually. Right, let's try that, the yellow one. I think it stands out a little bit better. Not sure. Okay, next one. I don't have a green one at the moment. Here's a blue one. Yeah. Let's try a blue one. A lot of people don't like blue. No. It's not so pleasing on the eye. I don't care what brightness it is. So at the moment, it's a toss-up between the white and the yellow. Now I think technically a white should be better because it contains all colours and it's going to get diffused by the grey smoke on the actual front panel. Yellow is already filtered out every other colour apart from yellow, but it depends on what the source brightness is. So let's just try, this is white again. and the yellow. I think the yellow is better because it stands out against the sort of off-white colour of the actual front panel itself. So let me try changing that resistor value and see what we get for the appearance of the brightness after that. Okay, let's put power on. Now that's without the increase in brightness. I'll just position it there, and let me just stick in the 1 meg in parallel. If I can. There it is there. And let me pull it off again. Yeah, it makes a little bit of a difference. I'd really like to know if you're seeing that on camera. So I'll put it back in and leave it in. I think yellow's the way to go. I'd like to have tried green, but I don't have a green. Well, that's my testing done. Quite happy with the white one with the slightly increased brightness. So I think I'm ready to move forward. And the next thing to do is to get that VFD off of the front panel, get the new display mounted up, and the STM32 board mounted on the back somewhere. Okay, this is going to take a while. There is just 100 odd or so, something like that. I'll come back. Well, let's freeing off the adhesive on the back of the VFD with some very, very thin spludgers, which are cutting through the glue just nicely. I think that's it. There we go. Wow. Yes. It was doubled up at this end. That's why it was a pain. This bit was easy enough. So I'll tidy this up and then we'll take a look at mounting the OLED. Well, that's the OLED tidied up as much as I need to. So that'll go away for safekeeping in case it ever needs to go back on. Right, so how's this for mounting an OLED? What I've actually done is I've put some copper wire from the display soldered onto the back of the display, because it just so happens on the back of the display you've got these little lugs here for clipping on the front bezel there. Well, they're tinned, so just a bit of solder there, and the same at the other end. And is able to solder on some copper wire. I've put on a right angled connector onto the PCB so that I can still get a connector in there. I want to be able to replace this OLED, especially if I try out a green one at some point, or because I've increased the brightness of it, it might deteriorate, so who knows. So it's relatively easy, there's no sticky tape, and I've made it so that the gap there, it stands off of the PCB just the right amount so that it butts up against the inside of the smoked perspex on the front there. So it should work out pretty good. And I can also adjust the height of it if I need to, just by pulling on it slightly, because there's enough give in those copper wires. Right, there's the Vero board attached. It's on copper wire standoffs, same as the OLED. And I used a nice little bit of Vero board there. It was exactly the right size, didn't need to cut it. It's exactly the right number of holes and length for the STM32 board. And it's in a socket, and I've put a small male header right along there that I can solder the wires on directly. So I don't think it looks too bad, and there's plenty of room behind this circuit board on the actual unit itself, no problem at all. And I should be able to get in the USB connector and SWD programming header here if I need to, no problem. Of course, I can always unplug it. So next thing, I'll go ahead and wire it up. Well, there it is, all wired up, all ready to go. And yeah, the ribbon cable here that goes away off to the OLED, I will tack that down, but I'm keeping it out of the way at the moment just so I can get these flat flexes fitted when I put it into the panel, because they're a bit awkward, these things. But everything else is okay. Okay, ready for a power up. Everything's connected, so let's go. Yes, it boots. Yes. Oh, yes. Oh, yes. That's pretty good. That's pretty good. Wow. Of course, being a bit narrower, it's a little bit harder to glance at the digits, but the alternative was a rather faint VFD. And it's pretty straight. It's centered. I'm well pleased with that. So let me just bolt up the front panel, and then I can tidy up that ribbon cable. And then you can see the STM32 board just coming into this void here perfectly. Plenty of space round about it, no problem whatsoever. So well pleased with that, and I can get at the SWD header and even the USB one if I want to, or I can just unplug it really, no problem at all. Well, there it is. That's my R6581T with a new lease of life. You can read the display now. Wow. Just a couple of questions I can answer. I've hunted high and low for a wider OLED display using the same chipset, because you know Mickle T's code is based around SSD 1322 chipset, and the next size up from this OLED is a 5.5 inch one, and really it's too big and you really have to shoehorn it in, and it's not pretty. So the only other way around it, which is something I am working on, I recently managed to convert Mickle T's C code into a Visual Studio project, and I've managed to compile it, so it's all running in Visual Studio now, and I'm in the midst of actually doing quite a lot of mods to the software to try and open it up to other controller ICs, but it may take a while. I've got a TFT display in mind, waiting on it coming, use a different controller, and it's quite a lot of work to convert it. The way Mickle T's original code works is the STM32 doesn't store character data at all. You might see the numbers 1.0000 and so on the display, but they're not stored or held in the STM32 memory at all like that. It's basically what he's doing, and it's very, very clever. He's reading the data stream that goes to the shift registers, etc. on the R6581T original board, and storing it as bitmap data in the STM32, then basically almost bit banging that out via SPI to the new display. And all of that is centered around the SSD 1322 chipset. But I've already done some work and I've managed to write some ASCII character recognition in the original code, which means I can store the character data, as you see there, in the STM32 memory, and that includes enunciators along the top and the second text row down the bottom there. A lot of work, but I am getting somewhere with that, and hopefully I can implement another controller. Because it's in Visual Studio, it's much easier for me to actually implement another controller IC. So anyway, thanks for watching, and remember, you can always comment down below, and don't forget to like and subscribe. It really does help the channel grow. There's plenty more repair videos on my channel, from the simple to the complex. Check them out, and thanks for watching.